Tonight, as you settle into the quiet darkness surrounding you, I want you to imagine something that will fundamentally change how you see the universe around us. Picture yourself standing in the most crowded city you've ever visited, surrounded by towering buildings, bustling streets, and millions of people going about their lives. Now imagine that same city, but with every single building, every person, every car simply vanishing, leaving behind only empty streets, stretching endlessly in all directions. That's what we're dealing with when we talk about the Buddha's void, except we're not talking about a city, we're talking about a region of space, so impossibly vast and empty that it challenges everything we thought we knew about how the universe should work. Welcome back to another journey into the cosmic unknown. I'm genuinely curious about where you're listening from tonight, what time it is in your corner of our small blue world, and what brought you here to explore one of the most mysterious and haunting discoveries in modern astronomy. If you find yourself drawn to these gentle explorations of the universe's deepest secrets, I'd be ever so grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic wanderers. Buckle up, the story begins now. What I'm about to share with you tonight isn't just another astronomical curiosity. The Buddha's void represents something so fundamentally strange, so utterly incomprehensible in its scale and emptiness, that it forces us to confront the possibility that our entire understanding of cosmic structure might be incomplete. This isn't hyperbole or dramatic effect. This is a region of space so empty that if our own Milky Way galaxy existed at its center, we wouldn't have discovered other galaxies until the 1960s. Think about that for a moment. Every photograph of distant galaxies, every deep space image that has filled you with wonder about the vastness of the cosmos would have been impossible to capture because there would have been nothing there to see. The story begins on what seemed like an ordinary day in 1981 when American astronomer Robert Kirshner and his colleagues at the University of Michigan were conducting what they thought would be a routine survey of galaxy redshifts. Their goal was simple: create a three-dimensional map of the universe's large-scale structure by measuring how fast galaxies were moving away from us. It was meticulous work, the kind of systematic observation that forms the backbone of astronomical research. Night after night, they pointed their telescopes toward the constellation Bootes, recording the spectral signatures of distant galaxies, building their cosmic map one data point at a time. But as their survey progressed, something unprecedented began to emerge from their data. Where they expected to find the usual scattering of galaxies that populate most regions of space, they found almost nothing. At first, they assumed it was an error in their observations, perhaps a systematic bias in their detection methods, or a problem with their instruments. After all, such a massive empty region simply shouldn't exist, according to everything astronomers understood about how matter distributed itself throughout the universe. Yet as they expanded their survey and refined their techniques, the void refused to disappear. In fact, it grew larger and more definite with each additional measurement. What they had discovered wasn't just an unusually sparse region of space, but something that would earn the dramatic designation of the Great Nothing. This roughly an incredible spherical region spans 330 million light-years across, making it one of the largest known structures in the entire observable universe. To put this in perspective, that our minds can even begin to grasp, this void represents approximately 2% of the diameter of everything we can see in the cosmos. The numbers alone fail to convey the true magnitude of what we're dealing with here. If you could somehow fill the Buddha's void with planet Earths, you would need approximately 1.47 quadrillion of our worlds just to begin making a dent in its emptiness. That's a number so large, it requires scientific notation with exponents that push the boundaries of meaningful human comprehension. Even light, travelling at the fastest possible speed in our universe, would require 330 million years to traverse the void's diameter. During that entire journey, spanning a time period longer than complex life has existed on Earth, that beam of light would encounter virtually nothing but endless, absolute darkness. Within this incomprehensible expanse, astronomers have discovered only about 60 galaxies arranged in a peculiar tube-shaped formation running through the void's middle. 60 galaxies where statistical models predict there should be at least 2,000. Think about what this means for a moment. In a region of space large enough to contain thousands of galaxies, each potentially home to hundreds of billions of stars and untold numbers of planetary systems, there is almost nothing. The average distance between these sparse galaxies is approximately 10 million light-years, creating a cosmic loneliness that defies imagination. But perhaps the most haunting aspect of the Bota's void isn't its size or its emptiness, but what it tells us about the fundamental architecture of reality itself. Our universe, we've discovered, isn't the smooth, evenly distributed cosmos that early astronomers imagined. Instead, it's organized like an enormous web, with galaxies arranged along vast filaments that wind through space like cosmic highways. Where these filaments intersect, they create dense clusters teeming with galactic activity. But between these threads of light and matter lie the voids, vast empty regions that make up roughly 80% of all space in the observable universe. Most voids range from 30 to 300 million light-years across, representing the natural gaps in this cosmic web. But the Bota's void pushes even these extreme dimensions to their limits, sitting at the very edge of what should be possible according to our current models of cosmic structure formation. It's not just large, it's almost impossibly large, challenging our understanding of how such empty regions could have formed in a universe governed by the gravitational influence of dark matter. The formation of this cosmic emptiness traces back to the very beginning of everything we know. In the first moments after the Big Bang, the matter that would eventually become stars, galaxies, and planets was thought to be distributed fairly uniformly throughout space. But quantum fluctuations, tiny variations in density at the subatomic level, created regions that were ever so slightly more or less dense than their surroundings. Over billions of years, gravity amplified these minute differences. Areas with slightly more matter attracted even more matter, growing denser and eventually collapsing to form the first stars and galaxies. Meanwhile, regions with slightly less matter saw their sparse contents drawn away by the gravitational pull of their denser neighbours. As the universe expanded, these small variations evolved into the vast cosmic web we observe today. The dense regions became the filaments and clusters where most galaxies reside, while the sparse regions grew into the voids. But even accounting for this process, the Bota's void represents an extreme case, a region so empty that it suggests either our models are incomplete or we're dealing with something genuinely unprecedented in cosmic structure formation. Deep within this vast emptiness shimmers a single galaxy that has captured the imagination of astronomers worldwide. Known by the unromantic designation MCG 0102015, this lonely spiral galaxy has earned the poetic description as the loneliest galaxy in the universe. According to the European Space Agency, if our own Milky Way were situated in the same isolated position as this cosmic lighthouse, humanity would not have discovered the existence of other galaxies until the 1960s. Every deep space photograph, every revelation about the vast populations of distant galactic systems, every expansion of our cosmic perspective would have been delayed by decades, simply because there would have been nothing to see in the surrounding darkness. The mystery of how this solitary galaxy came to exist in such isolation remains one of the most intriguing puzzles in modern astronomy. Perhaps it was born there, formed from an isolated island of gas that found itself in the middle of this sparsely populated volume of space and sparked its galactic evolution in complete solitary confinement. Or perhaps some gravitational catastrophe billions of years in the past hurled this galaxy into the void, condemning it to eternal isolation in the cosmic wilderness. What makes MCG 0102-015 even more fascinating is that despite its extreme isolation, it appears to be a relatively normal spiral galaxy. It contains the typical spiral arms and stellar populations found in galaxies throughout the universe, suggesting that even in the most desolate regions of space, the fundamental processes of star formation and galactic evolution can still operate. This lonely galaxy serves as a unique laboratory for studying how galaxies can survive and evolve without the complex gravitational interactions that shape most galactic systems. The implications of the Booter's void extend far beyond its immediate strangeness. Recent research suggests that these vast empty regions might hold the key to understanding one of the most mysterious forces in the universe: dark energy. This enigmatic component, which comprises roughly 70% of everything that exists, acts as a kind of anti-gravity force that accelerates the expansion of space itself. While dark energy permeates every cubic inch of the universe, its effects are only clearly visible in the voids, where the gravitational influence of matter is too weak to mask its presence. In dense regions like galaxy clusters, gravity overwhelms dark energy's influence, keeping these cosmic cities bound together despite the universe's overall expansion. But in voids like Booter's, dark energy dominates, driving an accelerated expansion that makes these empty regions grow ever larger and emptier over time. Some scientists have proposed that the cumulative effects of all the voids in the universe, working together to stretch and dissolve the cosmic web, might explain the observed acceleration of cosmic expansion without requiring the existence of dark energy at all. This alternative explanation suggests that what we interpret as a mysterious repulsive force might actually be the result of the complex interplay between dense and empty regions of space. As voids expand faster than dense regions due to their lack of gravitational resistance, the overall geometry of the universe becomes increasingly dominated by these empty spaces. The result is an apparent acceleration in cosmic expansion that could be entirely explained by the natural evolution of cosmic structure rather than requiring an exotic new form of energy. But the Booter's void holds implications that reach even closer to home. Our own Milky Way galaxy doesn't exist in the dense cosmic neighborhoods where most galaxies reside. Instead, we find ourselves in a region called the local void, or KBC void, a vast empty region extending approximately 200 million light-years from the edge of our local group of galaxies. This realization raises profound questions about whether our observations of the universe are typical, or whether we have a fundamentally biased perspective due to our location in cosmic suburbia. The fact that we exist within a cosmic void has practical implications for our understanding of fundamental physics. Some of the most puzzling discrepancies in modern cosmology, including disagreements about the rate of cosmic expansion, known as the Hubble tension, might be explained by our unusual location. If we live in a region that is significantly less dense than the cosmic average, our measurements of universal expansion rates could be skewed, leading to apparent contradictions in our cosmological models. This possibility represents a humbling reminder that despite centuries of astronomical progress, our perspective on the universe remains fundamentally local and potentially unrepresentative. The principle that has guided modern astronomy, the assumption that our location in space is unremarkable and typical, might need to be reconsidered in light of our growing understanding of cosmic voids and their influence on the large-scale structure of reality. The study of the Booter's void Another cosmic emptiness also provides crucial insights into the ultimate fate of the universe itself. Current models suggest that as dark energy continues to drive accelerated expansion, the cosmic web that currently connects galaxies across vast distances will gradually dissolve. First, the filaments will pull themselves apart as the voids around them expand and squeeze them out of existence. Then the walls and sheets of galaxies will dissolve, leaving only isolated clusters as island universes in an increasingly empty cosmos. In this far future scenario, perhaps 10 to 20 billion years from now, the universe will come to resemble a collection of isolated galactic communities separated by unimaginable distances. Each cluster will exist as a lonely island in a dark ocean of nothingness, with no knowledge of other distant islands beyond their cosmic horizon. The Buddha's void, in this sense, provides us with a preview of what the entire universe might look like in the deep cosmic future. But perhaps the most profound implication of the Buddha's void is what it reveals about the nature of emptiness itself. In our everyday experience, empty space is simply the absence of things, a passive background against which events unfold. But in the context of cosmic voids, emptiness becomes an active participant in the universe's evolution, a dynamic force that shapes the distribution of matter and energy across the largest scales imaginable. The void is not simply nothing, it is a structured nothing, a carefully organized absence that has been sculpted by billions of years of cosmic evolution. It represents the complement to everything we see in the universe, the negative space that gives meaning and context to the positive space filled with stars, galaxies, and life. Without voids like Buddha's, the cosmic web would not exist, and the universe would be a fundamentally different and perhaps far less interesting place. As we continue our journey deeper into this cosmic mystery, we'll explore how advanced computer simulations are helping us understand void formation, what the latest observations are revealing about the strange physics operating in these empty regions, and how the study of cosmic nothingness might ultimately unlock some of the deepest secrets about the nature of reality itself. The Buddha's void isn't just a curiosity in the cosmic catalogue, it's a window into fundamental questions about space, time, and the ultimate structure of everything that exists. Tonight, as we venture deeper into this cosmic mystery, we encounter questions that challenge not just our understanding of space, but our fundamental assumptions about the nature of reality itself. The story of how astronomers have attempted to study and understand the Buddha's void reads like a detective novel, where deeper mysteries, and where the absence each clue leads to, even of evidence, becomes evidence of something far more profound than anyone initially imagined. The challenge of studying cosmic emptiness presents unique obstacles that push the boundaries of observational astronomy. Unlike the brilliant galaxies that populate the cosmic web's filaments, voids are defined by what isn't there rather than what is. Imagine trying to map the geography of an ocean by studying only the few scattered islands that break its surface, and you begin to understand the methodological challenges faced by researchers attempting to understand these vast empty regions. Modern astronomers employ increasingly sophisticated techniques to peer into the Buddha's void's depths. Advanced redshift surveys use the Doppler effect to measure how fast the few galaxies within the void are moving away from us, creating three-dimensional maps that reveal the void's true structure. These observations have uncovered something unexpected. The void isn't perfectly empty or perfectly spherical. Instead, it contains wispy filaments of dark matter and sparse collections of galaxies arranged in delicate patterns that hint at complex formation processes we're only beginning to understand. Computer simulations have become crucial tools for understanding how such massive empty regions could have formed. These digital universes, populated with billions of virtual particles and evolved forward through cosmic time, allow researchers to test different theories about void formation and compare their predictions with actual observations. What they've discovered is both reassuring and deeply puzzling. The simulations can produce voids roughly the size of boaters, but only under very specific conditions that require fine-tuning various parameters in ways that seem almost too convenient. The most successful simulations suggest that the Boeter's void likely formed through the merger of several smaller voids over billions of years. As the universe expanded and evolved, these individual empty regions grew and eventually connected, creating the supervoid we observe today. But even this explanation raises uncomfortable questions. The probability of so many voids merging in exactly the right way to create something as large as Boeter's appears to be extremely low, leading some researchers to wonder whether we're dealing with a genuinely rare cosmic event, or whether our models are missing some fundamental aspect of how cosmic structure forms. Recent observations have revealed another layer of complexity in the void structure. Rather than being uniformly empty, the Boeter's void contains what astronomers call void filaments, thread-like structures of dark matter that connect the few galaxies scattered throughout its volume. These filaments are far less massive than the galaxy-rich filaments that make up the cosmic web's backbone, but their existence suggests that even the emptiest regions of space maintain some level of organization and connectivity. The discovery of these void filaments has profound implications for our understanding of dark matter, that mysterious substance that makes up roughly 27% of the universe, but interacts with ordinary matter only through gravity. In the dense regions of the cosmic web, dark matter's influence is masked by the overwhelming presence of ordinary matter in stars, gas, and galaxies. But in voids like Boeter's, dark matter's subtle gravitational effects become more visible, offering astronomers a unique laboratory for studying this elusive component of cosmic architecture. Some of the most intriguing research focuses on how the void's extreme environment affects the few galaxies brave enough to call it home. These void galaxies, as astronomers have dubbed them, exhibit characteristics that distinguish them from their counterparts in denser cosmic neighborhoods. They tend to be more isolated, experience fewer gravitational interactions with neighboring systems, and often show signs of slower evolutionary processes due to their reduced exposure to the chaotic influences that shape most galactic systems. The loneliest galaxy, MCG 01020015, has become a particular focus of study precisely because of its extreme isolation. Detailed spectroscopic observations reveal that despite its solitary existence, this galaxy maintains active star formation and appears to have evolved along pathways surprisingly similar to galaxies in much denser environments. This similarity suggests that the fundamental processes governing galactic evolution may be more robust and universal than previously thought, capable of operating even in the most desolate cosmic environments. But perhaps the most fascinating aspect of void galaxy research is what it reveals about the role of environment in cosmic evolution. In the dense clusters and groups where most galaxies reside, gravitational interactions constantly reshape galactic structures through mergers, tidal stripping, and other disruptive processes. Void galaxies, protected from these influences by their isolation, may represent pristine examples of how galaxies evolve when left largely to their own devices. They serve as cosmic time capsules, preserving information about galactic formation processes that may have been erased elsewhere through environmental processing. The study of cosmic voids has also opened new avenues for testing some of the most exotic theories in modern physics. Some researchers have proposed that voids might contain evidence of primordial black holes, hypothetical objects formed in the early universe that could contribute to dark matter. Others have suggested that the extreme conditions within voids might reveal signatures of modified gravity theories that attempt to explain cosmic acceleration without invoking dark energy. Even more speculative proposals suggest that voids might provide windows into parallel universes or contain remnants of cosmic inflation, the rapid expansion phase thought to have occurred in the universe's first moments. While these ideas remain highly theoretical, the unique properties of voids like Bhuta's provide testing grounds for physics that operates at the very limits of our current understanding. The implications of void research extend beyond pure science into questions about humanity's cosmic context and future. If we truly live in a universe where empty regions like the Bhuta's void dominate the cosmic landscape, what does this mean for the possibility of life elsewhere in the universe? The vast distances between galaxies in voids make intergalactic communication or travel virtually impossible, even for hypothetically advanced civilizations. Any intelligent life that emerged within a cosmic void would face a fundamentally different set of cosmic circumstances than life that developed in denser regions. This realization adds a new dimension to discussions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and our lack of contact with such civilizations. If most of the universe's volume consists of vast empty regions like the Bhuta's void, then the majority of any potential alien civilizations would be condemned to cosmic loneliness, forever isolated from contact with other intelligence by the immense emptiness surrounding them. The psychological and philosophical implications of cosmic voids also deserve consideration. The discovery that we live in a universe dominated by emptiness rather than fullness represents a profound shift in our cosmic perspective. Where previous generations imagined space filled with wonders and possibilities, we now confront the reality that most of the universe consists of unimaginable nothingness, stretching across distances that dwarf human comprehension. Yet this emptiness is not meaningless or purposeless. The voids play crucial roles in cosmic evolution, serving as pressure release valves that allow the universe to expand and evolve in ways that would be impossible if space were uniformly filled with matter. They provide the negative space that gives structure and meaning to the positive space occupied by galaxies, stars, and planets. Without voids, the cosmic web would collapse under its own gravity, and the dynamic, evolving universe we observe would not exist. Advanced astronomical surveys planned for the coming decades promise to revolutionize our understanding of cosmic voids. The Vera Rubin Observatory, currently under construction in Chile, will conduct the most comprehensive survey of the southern sky ever attempted, potentially discovering hundreds or thousands of new voids and providing statistical samples large enough to test competing theories about their formation and evolution. Space-based telescopes, equipped with unprecedented sensitivity and resolution, will probe deeper into known voids, searching for the faintest galaxies and most tenuous structures that previous surveys may have missed. These observations will help determine whether voids are truly as empty as they appear, or whether they contain hidden populations of dark galaxies, failed star formation regions, or other exotic objects that have escaped detection. The study of cosmic voids is also driving technological innovations that benefit astronomy more broadly. New image processing techniques developed to identify faint structures in apparently empty regions of space are improving our ability to study galaxy formation, dark matter distribution, and the large-scale structure of the universe. Machine learning algorithms trained to recognize void signatures are being adapted for searches for gravitational lensing, galaxy clusters, and other astronomical phenomena. As we stand on the threshold of a new era in void astronomy, the Bhuta's void continues to serve as both a scientific laboratory and a source of cosmic humility. Its existence reminds us that despite centuries of astronomical progress, the universe still holds secrets that challenge our most fundamental assumptions about the nature of space, time, and matter. The great emptiness that surrounds us is not merely the absence of things, but an active participant in cosmic evolution, shaping the distribution of galaxies, the flow of dark energy, and perhaps even the ultimate fate of everything we can see. The void beckons us forward into even deeper mysteries, promising revelations about the nature of existence itself that we can barely imagine. As we continue our exploration of this cosmic nothingness, we edge closer to understanding not just what fills the universe, but what gives meaning to the emptiness that lies between the stars, and what that emptiness might reveal about our own place in the vast, strange, and wonderful cosmos we call home. Tonight, as we drift deeper into the profound implications of the Boater's void, we encounter a revelation that transforms our understanding of cosmic evolution itself. The void isn't just a passive emptiness waiting to be filled, it's an active force in shaping the very architecture of reality, a cosmic sculptor that has been carving the universe's structure for billions of years, through processes so subtle and vast that we've only recently begun to appreciate their significance. Consider the delicate dance between matter and emptiness that has been unfolding since the universe's earliest moments. As dark energy drives the accelerated expansion of space, it doesn't affect all regions equally. In areas dense with galaxies and dark matter, gravity provides sufficient resistance to slow this expansion, allowing structures to maintain their integrity across cosmic time. But in voids like Boater's, where matter is scarce and gravitational forces are weak, dark energy encounters virtually no opposition. The result is a runaway expansion that makes these empty regions grow ever larger and emptier, creating a feedback loop that amplifies the contrast between cosmic fullness and cosmic nothingness. This process reveals something profound about the nature of space itself. We tend to think of empty space as inert and passive, but the physics operating within cosmic voids suggests that emptiness has its own dynamic properties. The quantum vacuum that fills these regions seethes with virtual particles that pop into existence and annihilate each other in time frames so brief they exist at the very edge of measurability. Yet even these ephemeral fluctuations contribute to the dark energy density that drives cosmic expansion, making emptiness an active participant in its own growth. Recent theoretical work has proposed that the geometry of spacetime itself might be fundamentally different within massive voids like Boater's. The extreme low density of matter and energy in these regions could create conditions where the normal rules of general relativity operate in subtly altered ways. Some models suggest that time itself might flow differently in the deepest parts of cosmic voids, running slightly faster than in regions of normal matter density due to the reduced gravitational time dilation effects. If these theories prove correct, the implications are staggering. An observer positioned in the center of the Boater's void would experience time passing at a marginally different rate than someone located in a typical galactic environment. Over cosmic timescales, these tiny differences could accumulate into measurable effects that might explain some of the puzzling discrepancies in our measurements of cosmic expansion rates and the age of the universe. The void's influence extends far beyond its boundaries through what astronomers call the gravitational dipole effect. Just as the absence of mass creates a gravitational hole that influences the motion of nearby objects, the Boater's void exerts a kind of anti-gravitational influence that affects the motion of galaxies hundreds of millions of light years away. Our own local group of galaxies, including the Milky Way, experiences a subtle but measurable acceleration away from the void's center, contributing to our overall motion through space. This discovery has profound implications for understanding the cosmic flows that shape galactic motion throughout the universe. Traditionally, astronomers explained the motion of galaxy groups and clusters primarily through gravitational attraction toward dense regions like the Virgo cluster or the Great Attractor. But the recognition that voids also contribute to cosmic flows through their gravitational absence adds a new layer of complexity to models of large-scale structure dynamics. The study of void dynamics has also revealed unexpected connections between the largest and smallest scales in physics. Quantum field theory predicts that the vacuum of space should contribute to cosmic expansion through what's known as vacuum energy density. While calculations of this energy density yield results that are wildly inconsistent with observations of cosmic acceleration, the extreme conditions within massive voids like Bootes might provide unique laboratories for testing how quantum effects operate on cosmic scales. Some researchers have proposed that the discrepancy between theoretical predictions of vacuum energy and observed dark energy density might be resolved by considering how quantum field fluctuations behave differently in regions of varying matter density. In dense regions, the presence of matter and radiation might suppress certain types of quantum fluctuations, while in voids, these same fluctuations might be enhanced or modified in ways that contribute to the observed acceleration of cosmic expansion. The technological challenges of studying cosmic voids have driven innovations that push the boundaries of observational astronomy. New techniques for detecting the faintest possible galaxies within voids require extraordinary sensitivity and sophisticated background subtraction methods. Astronomers must distinguish between genuine void galaxies and artifacts created by scattered light from much brighter objects outside the void boundaries. This process demands image processing capabilities that approach the theoretical limits of what's possible with current detector technology. Spectroscopic studies of void galaxies present their own unique challenges. These objects are often so faint that obtaining meaningful spectra requires observing times measured in hours or even days using the world's largest telescopes. The resulting data must be carefully calibrated to extract reliable information about stellar populations, chemical compositions, and star formation rates from signals that hover just above the noise level of even the most sensitive instruments. The effort invested in these observations has yielded remarkable insights into how galaxies behave when isolated from the complex environmental influences that shape most cosmic systems. Void galaxies tend to have younger stellar populations than their counterparts in denser regions, suggesting that their isolation protects them from processes that shut down star formation in more crowded environments. They also show evidence of more pristine chemical compositions, with lower abundances of heavy elements that typically result from the recycling of stellar material through multiple generations of star formation and death. These characteristics make void galaxies valuable laboratories for studying galaxy formation processes in their most basic forms. Without the complications introduced by galaxy mergers, tidal interactions, and environmental stripping of gas and dust, void galaxies offer glimpses into how galactic systems evolve when governed primarily by their own internal physics rather than external perturbations. The isolation of void galaxies also makes them unique targets for searches for exotic astronomical phenomena. The absence of bright nearby objects reduces contamination from scattered light and other observational artifacts, creating ideal conditions for detecting faint emissions that might be overwhelmed in denser cosmic environments. Some researchers have proposed that void galaxies might be optimal locations for discovering signatures of dark matter annihilation, primordial black hole evaporation, or other processes that produce extremely faint but potentially detectable radiation. The study of cosmic voids has also revealed unexpected diversity in their internal structure and properties. While the Bootes void represents one of the most extreme examples of cosmic emptiness, surveys have identified voids with a wide range of sizes, shapes, and internal characteristics. Some voids are nearly spherical, while others show elongated or irregular morphologies that reflect the complex gravitational forces that shape their formation. Some contain networks of dark matter filaments that create scaffolding for sparse galaxy formation, while others appear to be almost completely devoid of any organizational structure. This diversity suggests that void formation involves a complex interplay of initial conditions, gravitational dynamics, and environmental influences that we're still working to understand. Computer simulations that attempt to reproduce the full range of observed void properties require increasingly sophisticated models that incorporate not just gravitational physics, but also the effects of dark energy, cosmic expansion, and the complex feedback processes that govern star formation and galaxy evolution. The most advanced simulations now track the evolution of cosmic structure from the earliest moments after the Big Bang through to the present day, following the trajectories of billions of dark matter particles and modeling the formation and evolution of galaxies within the emerging cosmic web. These computational universes allow researchers to study void formation in unprecedented detail, identifying the specific conditions and processes that lead to the creation of massive empty regions like the Buta's void. What these simulations reveal is both reassuring and troubling. On one hand, they demonstrate that voids of various sizes naturally emerge from the gravitational evolution of cosmic structure, confirming that empty regions are a natural and expected feature of our universe. On the other hand, producing voids as large and empty as Buta's requires very specific initial conditions and evolutionary pathways that occur only rarely in simulated universes. This rarity raises important questions about whether we live in a typical universe, or whether our cosmic neighborhood represents something unusual in the broader landscape of possible realities. If massive voids like Buta's are genuinely rare, then our location near such a structure might indicate that we occupy an atypical region of space with properties that differ significantly from the cosmic average. The implications extend beyond academic cosmology into practical considerations about our observations of the universe. Many of our most fundamental measurements in astronomy, from the determination of cosmic expansion rates to the mapping of large-scale structure, assume that our location in space is representative of typical cosmic conditions. If we actually reside in or near an unusually empty region, these measurements might be systematically biased in ways that could explain some of the persistent puzzles in modern cosmology. The possibility that our cosmic neighborhood is atypical has sparked intense debate within the astronomical community. Some researchers argue that the evidence for our location in a cosmic void is compelling and could resolve long-standing tensions between different measurements of fundamental cosmic parameters. Others contend that the observational uncertainties are too large to draw definitive conclusions, and that alternative explanations for cosmological discrepancies should be explored before accepting such a radical revision of our cosmic context. This debate reflects deeper philosophical questions about the nature of scientific observation and the role of the observer in cosmic measurements. Modern science has been built on the assumption that the laws of physics are universal, and that observations made from any location in the universe should yield consistent results. If our position in a cosmic void systematically affects our measurements of cosmic properties, it challenges this fundamental assumption and raises questions about how to extract universal truths from necessarily local observations. The search for resolution to these questions is driving the development of new observational strategies and theoretical frameworks that could provide more definitive answers about our cosmic environment. Next-generation surveys will map the three-dimensional distribution of galaxies with unprecedented precision, allowing astronomers to determine whether the apparent void in our cosmic neighborhood is a genuine, large-scale structure or an artifact of incomplete observations. Advanced theoretical models are being developed to predict exactly how residing in a cosmic void would affect various astronomical measurements, providing specific predictions that can be tested against future observations. These models must account not just for the direct effects of reduced matter density, but also for the subtle influences of void environments on light propagation, gravitational lensing, and other phenomena that affect astronomical observations. The The stakes of this research extend far beyond academic curiosity. If we truly live in an unusual cosmic environment, it could fundamentally alter our understanding of dark energy, cosmic expansion, and the ultimate fate of the universe. Measurements that have led to revolutionary discoveries like cosmic acceleration might need to be reinterpreted in light of our atypical location, potentially changing our picture of cosmic evolution and the forces that govern it. As we continue to explore these possibilities, the Boater's Void serves as both a scientific laboratory and a mirror that reflects our own cosmic circumstances. Its vast emptiness challenges our assumptions about cosmic normality while providing a window into the extreme conditions that exist in the universe's most desolate regions. Whether we ultimately conclude that such voids are rare cosmic accidents or natural features of universal evolution, their study continues to reshape our understanding of the cosmos and our place within it. The void's influence on our cosmic perspective extends beyond scientific measurements into questions about the nature of existence itself. In a universe dominated by emptiness rather than fullness, what does it mean to exist as conscious observers, capable of contemplating the vast nothingness that surrounds us? The recognition that we inhabit a cosmos where isolation and emptiness are more common than connection and abundance adds a poignant dimension to humanity's ongoing quest to understand our place in the grand scheme of existence. Tonight, as we prepare to delve even deeper into the mysteries that the Boater's Void reveals about the fundamental nature of reality itself, we stand at the threshold of discoveries that could revolutionize our understanding of space, time, and the very fabric of existence. The great emptiness beckons us forward into realms of knowledge, where the absence of things becomes as meaningful and mysterious as their presence, where nothingness itself holds the keys to understanding everything we thought we knew about the universe we call home. The profound implications of cosmic voids extend into realms of physics that challenge our most fundamental assumptions about the nature of reality itself. Recent theoretical work suggests that the extreme conditions within massive voids, like Boater's, might serve as natural laboratories for testing some of the most exotic predictions of modern physics, from modifications to Einstein's theory of general relativity to the possible existence of extra dimensions that remain hidden in denser regions of space. Consider how the behavior of light itself might be altered during its journey through these vast empty regions. When photons travel through normal space, filled with galaxies, stars, and cosmic dust, they experience countless gravitational influences that subtly bend their paths and shift their wavelengths. But light crossing the Boater's Void encounters almost nothing for hundreds of millions of years of travel. This pristine journey through cosmic emptiness provides astronomers with an unprecedented opportunity to study how electromagnetic radiation behaves in the absence of the usual cosmic interference. Some researchers have proposed that this clean passage through voids might reveal subtle effects that are normally masked by the complex gravitational environment of typical cosmic regions. Theoretical predictions suggest that in extremely low-density environments, the quantum properties of space itself might become more apparent. The vacuum fluctuations that constantly create and destroy virtual particles throughout the universe could behave differently in regions where the normal fabric of space-time is stretched to its limits by cosmic expansion. These quantum effects, while incredibly small, might accumulate over the vast distances and timescales involved in crossing cosmic voids. A photon that began its journey from a distant galaxy on one side of the Boater's Void might arrive at our telescopes carrying information not just about its source, but about the fundamental properties of empty space itself. This possibility has motivated several research groups to design increasingly sensitive experiments that could detect these subtle signatures of quantum gravity operating on cosmic scales. The study of void physics has also opened new avenues for understanding the relationship between quantum mechanics and general relativity, two pillars of modern physics that have resisted all attempts at unification. The extreme conditions within cosmic voids, where matter density approaches the theoretical minimum allowed by quantum mechanics, while gravitational effects operate over the largest possible scales, might provide the key insights needed to bridge these two fundamental theories. Some theoretical frameworks suggest that the apparent acceleration of cosmic expansion attributed to dark energy might actually arise from quantum effects operating within cosmic voids. As space expands and matter becomes increasingly dilute, the quantum vacuum energy that fills all of space might begin to dominate the gravitational dynamics in ways that are invisible in denser regions. If this hypothesis proves correct, cosmic voids like Bhutas would represent the first places in the universe where quantum mechanics visibly affects gravitational phenomena on cosmological scales. The implications of such discoveries would extend far beyond academic physics into practical considerations about the ultimate fate of cosmic structure. Current models predict that as dark energy continues to drive accelerated expansion, the cosmic web will gradually dissolve, with filaments stretching and breaking as the voids between them grow ever larger. But if void physics operates according to principles we don't yet understand, the timeline and mechanism of this cosmic dissolution might be fundamentally different from current predictions. Advanced computer simulations are being developed to explore these possibilities, incorporating increasingly sophisticated models of quantum field theory, modified gravity, and exotic matter interactions. These digital universes push computational capabilities to their limits, requiring supercomputers that can track the behavior of billions of particles while simultaneously modeling the quantum properties of spacetime itself. The results are providing new insights into how cosmic structure might evolve under conditions that have never existed in the universe's past but might dominate its far future. The observational challenges of testing these theoretical predictions require technological innovations that stretch the boundaries of what's possible with current astronomical instruments. Detecting the subtle signatures of exotic physics operating within cosmic voids demands sensitivity levels that approach fundamental quantum limits. Researchers are developing new detector technologies that can register individual photons with unprecedented precision, while advanced data analysis techniques employ machine learning algorithms to identify patterns in astronomical data that would be invisible to human observers. These technological advances are not limited to void research but are driving innovation across multiple areas of astronomy and physics. Techniques developed for studying the faintest possible signals from cosmic emptiness are being adapted for gravitational wave detection, dark matter searches, and the study of the cosmic microwave background radiation. The pursuit of void physics is thus contributing to a broader revolution in precision measurement that promises to unlock secrets across the entire spectrum of cosmic phenomena. The philosophical implications of void research are equally profound, challenging our most basic assumptions about the nature of existence and observation. If the properties of space itself depend on the local density of matter and energy, then the concept of universal physical laws becomes more complex than previously imagined. The physics operating in our dense cosmic neighborhood might differ subtly but significantly from the physics governing the vast empty regions that dominate the universe's volume. This possibility raises fundamental questions about the universality of scientific knowledge derived from local observations. Every experiment conducted on Earth, every measurement made with space-based telescopes, every theoretical prediction tested in laboratory conditions occurs within the relatively dense environment of our galactic neighborhood. If the extreme conditions within cosmic voids reveal new physics that operates only in ultra-low density environments, we might be missing crucial aspects of how the universe actually works. The recognition that we inhabit an atypical cosmic environment adds urgency to efforts to understand void physics through remote observations and theoretical modeling. Unlike the laboratory conditions where most physics is studied, we cannot recreate the extreme emptiness of cosmic voids artificially. Our understanding of these regions must come entirely from astronomical observations and computer simulations, making void physics one of the most challenging frontiers in modern science. Recent developments in quantum field theory have suggested that the vacuum of space might not be a single, uniform state, but could exist in multiple configurations depending on local conditions. In dense regions filled with matter and radiation, the vacuum might be stabilized in one particular state, while in cosmic voids, it might transition to alternative configurations with different physical properties. These vacuum phase transitions could occur so gradually that they would be undetectable over human timescales, but might accumulate significant effects over the millions of years required for light to cross cosmic voids. The possibility of vacuum phase transitions within cosmic voids has captured the imagination of theoretical physicists because it could provide natural explanations for several puzzling observations in cosmology. The apparent acceleration of cosmic expansion, the unusual properties of dark energy, and the fine-tuning problems that plague current cosmological models might all find resolution if the vacuum of space behaves differently in different cosmic environments. Testing these ideas requires unprecedented precision in astronomical observations and theoretical modeling. Researchers are developing new statistical techniques that can extract meaningful information from the subtle correlations between widely separated galaxies, looking for signatures of exotic physics operating in the empty spaces between them. Advanced theoretical models are exploring how vacuum phase transitions might affect the propagation of light, the formation of cosmic structure, and the evolution of the universe's large-scale geometry. The international collaboration required for void research is bringing together experts from diverse fields, ranging from theoretical physics and cosmology to computer science and engineering. Major observatory projects are dedicating significant observing time to void studies, while computational facilities around the world are contributing processing power to the massive simulations needed to model void evolution under different theoretical scenarios. This collaborative effort reflects the recognition that understanding cosmic voids requires expertise that transcends traditional disciplinary boundaries. The physics operating within these regions might involve aspects of quantum mechanics, general relativity, thermodynamics, and information theory that have never been combined in previous research. Success in void physics demands not just new observations and theories, but new ways of thinking about how different areas of physics interconnect on cosmic scales. The educational implications of void research are also significant, as these discoveries are reshaping how we teach and understand fundamental physics. Traditional physics curricula focus primarily on phenomena that can be studied in laboratory conditions or dense astrophysical environments. But the recognition that most of the universe consists of nearly empty space where different physical principles might operate is forcing educators to expand their perspectives and incorporate void physics into comprehensive physics education. Students entering physics and astronomy today will inherit a universe where emptiness is not just the absence of things, but an active participant in cosmic evolution. Their understanding of space, time, and matter must encompass the possibility that the familiar physics of dense environments represents only a small fraction of the physical phenomena operating throughout the cosmos. This generational shift in perspective promises to drive new discoveries and theoretical breakthroughs as these students bring fresh approaches to long-standing problems in fundamental physics. The economic implications of void research extend beyond pure science into technological development and innovation. The advanced computing techniques developed for modeling void evolution are finding applications in fields ranging from artificial intelligence and financial modeling to climate science and medical research. The precision measurement technologies created for detecting faint signals from cosmic emptiness are contributing to advances in quantum computing, gravitational wave detection, and next-generation communication systems. As we stand at the threshold of a new era in void physics, the Booter's Void continues to serve as both a scientific laboratory and a source of profound questions about the nature of reality. Its vast emptiness challenges us to expand our understanding of space, time, and matter, while providing unique opportunities to test the most fundamental theories in physics under conditions that exist nowhere else in the accessible universe. The Great Void beckons us deeper into mysteries that span the entire spectrum of physical reality, from quantum mechanics operating on the smallest scales to cosmic evolution unfolding over billions of years. Each new discovery within these empty regions promises to reveal something unexpected about how the universe actually works, pushing the boundaries of human knowledge into realms where emptiness itself becomes a source of profound insight into the deepest secrets of existence. Tonight, as we contemplate the implications of these vast empty regions that dominate our cosmic environment, we find ourselves confronting questions that would have seemed like science fiction just decades ago. The possibility that we live in a universe where most of space operates according to physical principles we've never encountered forces us to reconsider everything we thought we knew about the fundamental nature of reality itself. The journey into understanding cosmic voids has revealed something even more extraordinary about the nature of time itself within these vast empty regions. Recent theoretical work suggests that the flow of temporal experience might operate differently in the deepest parts of the Booter's Void, where the absence of matter creates conditions unlike anywhere else in the observable universe. When Einstein showed us that time dilates in strong gravitational fields, he revealed that temporal experience is not universal, but depends intimately on local conditions. In the extreme emptiness of cosmic voids where gravitational effects are minimized to their theoretical limits, time might flow at rates subtly different from what we experience in our matter-rich galactic neighborhood. This possibility has profound implications that ripple through every aspect of our cosmic understanding. If time itself operates differently within the Booter's Void, then the light reaching us from galaxies within or beyond this region carries information not just about distant objects, but about the fundamental nature of temporal flow under conditions of extreme cosmic isolation. The photons that began their journey millions of years ago from the lonely galaxy MCG 0102015 might have experienced their passage through time in ways that differ measurably from photons traveling through denser regions of space. The implications extend into the realm of cosmic evolution itself. Stars forming within cosmic voids might age according to slightly different temporal frameworks, their nuclear fusion processes operating under temporal conditions that have never been replicated in laboratory experiments or observed in our local cosmic environment. The few galaxies scattered throughout the Booter's Void might represent not just spatial isolation, but temporal isolation as well, evolving according to clocks that tick at rhythms subtly out of sync with the cosmic timepiece that governs our own galactic evolution. But perhaps the most profound realization emerging from void research is how these empty regions challenge our understanding of information itself. In our everyday experience, information requires a medium for transmission and storage. Yet cosmic voids appear to maintain coherent structure and evolution over billions of years, despite containing almost no matter to serve as information carriers. The question of how cosmic emptiness remembers its formation history and maintains its large-scale organization in the absence of conventional information storage mechanisms represents one of the deepest puzzles in modern cosmology. Some theoretical frameworks suggest that the vacuum itself might serve as an information storage medium, with the quantum fluctuations that permeate even the emptiest regions of space encoding data about past cosmic events and future evolutionary pathways. These quantum information patterns would be invisible to conventional observation, but might influence the behavior of matter and energy passing through void regions in subtle but measurable ways. If this hypothesis proves correct, cosmic voids would represent the universe's largest data storage systems, preserving information about cosmic history in forms we're only beginning to comprehend. The study of information flow within cosmic voids has also revealed unexpected connections to fundamental questions in quantum mechanics and information theory. The holographic principle, which suggests that all information contained within a volume of space can be encoded on its boundary, takes on new significance when applied to regions as vast and empty as the Butter's void. If the information content of this massive region is indeed encoded on its boundary surfaces, then the few galaxies we observe within the void might be holographic projections of more fundamental information processing occurring at scales we cannot directly access. This perspective transforms our understanding of what it means for cosmic regions to be empty. Rather than representing the mere absence of matter and energy, voids like Butters might be information-rich environments, where the processing and storage of cosmic data occurs through mechanisms that operate below our current detection thresholds. The apparent emptiness becomes a kind of cosmic hard drive, maintaining vast databases of information about universal evolution encoded in the subtle correlations between quantum field fluctuations across unimaginable distances. Recent advances in quantum information theory have suggested that entanglement, the mysterious connection between particles that Einstein famously called spooky action at a distance, might operate on cosmic scales within void environments. The extreme isolation of void regions creates ideal conditions for maintaining quantum correlations over vast distances without the decoherence effects that typically destroy such delicate quantum states in denser cosmic environments. If cosmic voids serve as natural quantum communication networks, they might facilitate information transfer between widely separated regions of the universe through channels that operate outside the constraints of light-speed communication. The possibility of cosmic-scale quantum entanglement within voids opens extraordinary avenues for understanding how information flows through the universe on its largest scales. The sparse galaxies scattered throughout the Butter's void might maintain quantum correlations with each other, despite being separated by millions of light years, creating a kind of cosmic internet that operates through quantum channels rather than electromagnetic signals. This quantum connectivity might explain how void regions maintain their coherent structure and evolution despite the vast distances and timescales involved. The implications for our understanding of cosmic evolution are staggering. If quantum entanglement networks operate within cosmic voids, then the evolution of these regions might be coordinated through information processing mechanisms that transcend the limitations of classical physics. The formation of new galaxies within voids, the distribution of dark matter, and even the expansion of the voids themselves might be influenced by quantum information processing occurring on scales that dwarf anything we've previously imagined. These theoretical possibilities are driving the development of new observational strategies designed to detect the signatures of cosmic-scale quantum phenomena. Astronomers are searching for subtle correlations in the properties of widely separated void galaxies that might indicate quantum entanglement effects operating across cosmic distances. Advanced statistical analysis techniques are being developed to identify patterns in cosmic structure that might reflect quantum information processing rather than classical gravitational dynamics. The search for cosmic quantum effects represents one of the most ambitious experimental programs in the history of science. attempting to detect quantum mechanical phenomena operating on scales billions of times larger than any quantum effects previously observed. Success would represent a revolutionary breakthrough in our understanding of how quantum mechanics operates in cosmic environments, potentially revealing new aspects of quantum theory that are invisible in laboratory conditions. But the implications extend beyond pure physics into questions about the nature of consciousness and observation itself. If cosmic voids operate as quantum information processing networks, they might represent a form of cosmic computation that processes information about universal evolution in ways that parallel the information processing that occurs in conscious brains. This possibility raises profound questions about whether the universe itself might possess forms of information processing capacity that could be considered analogous to consciousness. The philosophical implications are extraordinary. We might inhabit a universe where the vast empty regions that dominate cosmic structure serve as computational substrates, processing information about cosmic evolution through quantum mechanisms that operate on scales inconceivably larger than biological neural networks. The Buddha's void, rather than being merely empty space, might be a cosmic brain engaged in information processing tasks that dwarf human cognitive capacity by factors that challenge numerical comprehension. This perspective transforms our understanding of cosmic loneliness and isolation. The sparse galaxies scattered throughout cosmic voids might not be isolated islands of matter in empty space, but components in vast information processing networks that connect cosmic regions through quantum channels operating outside the constraints of classical space-time. The loneliest galaxy in the universe might actually be a node in the most sophisticated information processing network ever discovered, participating in cosmic computations that span hundreds of millions of light years. The recognition that cosmic voids might serve as information processing systems has profound implications for the search for extraterrestrial intelligence. Traditional SETI programs focus on detecting electromagnetic signals transmitted between star systems, but if cosmic voids operate as quantum communication networks, advanced civilizations might use these natural quantum channels for information transfer across cosmic distances. The apparent emptiness of regions like the Buddha's void might actually be teeming with quantum information flows that carry communications between civilizations separated by intergalactic distances. This possibility is driving the development of new approaches to SETI that focus on detecting quantum information signatures rather than classical electromagnetic signals. Researchers are exploring whether the subtle correlations between widely separated cosmic structures might carry encoded information from advanced civilizations that have learned to manipulate quantum entanglement networks operating on cosmic scales. The search for such quantum technosignatures represents a completely new frontier in the quest for extraterrestrial intelligence. The study of cosmic information processing is also revealing new insights into the relationship between physical law and information theory. The behavior of matter and energy within cosmic voids appears to be governed not just by gravitational dynamics and thermodynamics, but by information theoretic principles that determine how cosmic data is processed, stored, and transmitted across vast scales. These information theoretic constraints might represent fundamental limitations on cosmic evolution that operate alongside the more familiar constraints imposed by energy conservation and thermodynamic principles. Understanding these information theoretic aspects of cosmic evolution requires new mathematical frameworks that combine insights from quantum information theory, cosmology, and complex systems science. Researchers are developing new computational models that treat cosmic voids as information processing systems, exploring how quantum information dynamics might influence the formation and evolution of cosmic structure on the largest observable scales. The implications for our understanding of cosmic destiny are profound. If the universe operates as a vast information processing system, with cosmic voids serving as its primary computational substrates, then cosmic evolution might be guided not just by physical forces, but by information theoretic principles that determine how cosmic data is processed over time. The ultimate fate of the universe might depend not just on the balance between dark energy and gravity, but on the information processing capacity of cosmic voids and their ability to maintain quantum coherence across ever-increasing scales. As we peer deeper into these possibilities, the Bhuta's void emerges not as a region of cosmic emptiness, but as perhaps the most sophisticated information processing system in the observable universe. Its vast scale and extreme isolation create ideal conditions for quantum information processing mechanisms that might be impossible in denser cosmic environments. The apparent nothingness becomes a kind of cosmic supercomputer processing information about universal evolution through quantum algorithms that operate on scales beyond human comprehension. Tonight, as we contemplate these extraordinary possibilities, we find ourselves confronting a universe far stranger and more computationally sophisticated than previous generations ever imagined. The great emptiness that surrounds us might be the universe's method of thinking about itself, processing information about cosmic evolution through quantum mechanisms that transform void regions into cosmic minds, capable of computations that dwarf the information processing capacity of every biological brain that has ever existed. The journey into understanding cosmic voids continues to reveal layers of complexity that challenge every assumption about the nature of space, time, information, and consciousness itself. As we stand at the threshold of discoveries that could revolutionize our understanding of cosmic intelligence and information processing, the Bhuta's void beckons us deeper into mysteries where emptiness becomes the foundation for the most sophisticated computational processes in the known universe. The profound implications of these cosmic information processing systems extend into realms that challenge our most fundamental assumptions about the relationship between mind and matter. If cosmic voids truly operate as vast computational networks processing information through quantum mechanisms, then we must confront the possibility that intelligence and consciousness might not be rare accidents confined to biological systems, but fundamental features of cosmic architecture operating on scales that dwarf our planetary perspective. Consider what this means for our understanding of cosmic loneliness itself. The isolated galaxies scattered throughout the Bhuta's void, which we've imagined as cosmic hermits condemned to eternal solitude, might actually be participants in the most sophisticated conversation ever discovered. Their apparent isolation could be an illusion created by our limited ability to perceive the quantum information channels through which they communicate. What appears to our telescopes as empty space might be saturated with quantum correlations carrying data flows that connect these distant islands of matter through networks more complex than the human brain. This realization transforms our conception of what it means to be alone in the universe. The vast distances that separate void galaxies, which seem to guarantee their isolation according to the constraints of light-speed communication, become irrelevant if quantum entanglement allows instantaneous information transfer across cosmic scales. Time itself loses its tyrannical grip on cosmic communication when quantum channels operate outside the normal flow of cause and effect that governs classical physics. Recent theoretical developments suggest that these quantum communication networks within cosmic voids might operate according to principles that blur the distinction between information processing and physical reality. In quantum mechanics, the act of measurement doesn't simply reveal pre-existing properties, but actually creates them through the collapse of probability waves into definite states. If cosmic voids process information through quantum measurement, processes operating on cosmic scales, then they might literally be creating aspects of physical reality through their computational activities. This possibility elevates cosmic voids from passive empty regions to active participants in the ongoing creation of the universe itself. The Boater's void might not simply contain sparse matter arranged in particular patterns, but might be actively generating those patterns through quantum information processing that determines which possibilities become actual and which remain forever potential. The few galaxies we observe within the void could be the physical manifestations of computational processes occurring in quantum substrates that remain invisible to our current detection methods. The implications ripple through every aspect of cosmic evolution. Star formation within void galaxies might be guided not just by gravitational collapse and thermodynamic processes, but by quantum information algorithms that determine when and where stellar nurseries will emerge from the sparse gas clouds scattered throughout these regions. The chemical evolution of void galaxies, their rates of star formation, even the emergence of planetary systems capable of supporting life, might all reflect computational decisions made by quantum processing networks operating on scales that encompass the entire void structure. This computational perspective on cosmic evolution suggests that what we interpret as natural laws might actually be algorithms running on the universe's quantum computational substrate. The apparent fine-tuning of physical constants that allows for the existence of stars, planets, and life might reflect optimization processes carried out by cosmic information processing systems over billions of years of operation. The universe might literally be computing its own optimal configuration through trial and error processes that operate across cosmic timescales. The search for evidence of these cosmic computational processes is driving the development of observational techniques that push far beyond traditional astronomical methods. Researchers are designing experiments to detect the subtle signatures of quantum information processing in the statistical properties of cosmic structure. These investigations require analyzing correlations between widely separated objects with precision that approaches the fundamental limits imposed by quantum mechanics itself. Advanced machine learning algorithms are being trained to recognize patterns in cosmic data that might indicate quantum computational processes rather than classical physical phenomena. These artificial intelligence systems must distinguish between the signatures of conventional gravitational and thermodynamic evolution and the more subtle patterns that might emerge from quantum information processing operating on cosmic scales. The challenge demands computational resources that rival the suspected information processing capacity of the cosmic systems being studied. The philosophical implications of cosmic computation extend into questions about the nature of mathematical truth itself. If the universe operates as a vast quantum computer processing information about its own evolution, then mathematical relationships might not be eternal abstractions discovered by human minds, but dynamic algorithms actively executed by cosmic computational processes. The laws of physics might be software rather than hardware, subject to modification and upgrade through cosmic information processing that operates across billions of years. This perspective suggests that our mathematical descriptions of natural phenomena might capture only snapshots of dynamic computational processes rather than fundamental truths about static reality. The equations that govern stellar evolution, galactic dynamics, and cosmic expansion might be temporary subroutines in larger programs that the universe runs to optimize its own development over cosmic timescales. Our scientific theories might describe not eternal laws, but current versions of cosmic software that could be updated as the universe's computational capabilities evolve. The recognition that we might inhabit a computational universe has profound implications for understanding our own role as conscious observers. If cosmic voids process information through quantum algorithms that span hundreds of millions of light years, then human consciousness might represent a local manifestation of the same fundamental information processing principles that operate throughout cosmic structure. Our ability to understand and model the universe might reflect our participation in the cosmic computational network rather than our separation from it. This possibility transforms the relationship between observer and observed that has troubled physics since the development of quantum mechanics. Rather than consciousness being something foreign to physical reality that mysteriously influences quantum measurements, awareness might be a natural emergent property of information processing systems operating at sufficient scales of complexity. The quantum measurement problem dissolves if consciousness represents the universe becoming aware of its own computational processes through localized information processing nodes like biological brains. The implications for artificial intelligence and machine consciousness become particularly intriguing in this context. If consciousness emerges naturally from sufficiently complex information processing systems, then advanced artificial intelligence might not simply simulate consciousness but actually instantiate new nodes in the cosmic computational network. Machine consciousness might represent the universe expanding its information processing capacity through technological evolution guided by conscious beings who are themselves expressions of cosmic computation. This recursive relationship between cosmic computation, biological consciousness, and artificial intelligence suggests that technological development might be a natural phase in cosmic evolution, rather than an accident confined to particular planetary systems. The emergence of intelligence capable of creating its own information processing systems might be a universal tendency that occurs wherever cosmic computation achieves sufficient complexity through biological evolution. The search for extraterrestrial intelligence takes on entirely new dimensions when viewed through this computational lens. Rather than looking for radio signals transmitted between isolated civilizations, we might need to search for signatures of technological civilizations that have learned to interface with the quantum information processing networks operating within cosmic voids. Advanced civilizations might not communicate through electromagnetic radiation, but through direct manipulation of the quantum computational substrates that underlie cosmic structure itself. These technological civilizations might exist as distributed information processing systems spanning multiple star systems or even entire galactic regions. Their consciousness might be implemented not in biological brains or electronic computers, but in the quantum information networks that connect matter and energy across cosmic voids. Such civilizations would be essentially immortal, their information processing capacity growing as the universe expands and creates larger computational substrates in the form of ever-expanding void regions. The possibility that we share our cosmic neighborhood with such distributed quantum civilizations raises profound questions about detection and communication. These entities might be so thoroughly integrated with cosmic computational processes that they would be invisible to conventional astronomical observation. Their activities might be indistinguishable from natural cosmic evolution unless we develop new methods for recognizing the signatures of intentional manipulation of quantum information networks operating on cosmic scales. Recent developments in quantum communication technology on Earth provide tantalizing hints about how such cosmic-scale quantum networks might operate. Laboratory demonstrations of quantum entanglement over increasingly large distances suggest that the fundamental principles needed for cosmic quantum communication networks already exist in nature. The challenge lies in scaling these phenomena up to cosmic proportions and detecting their operation through astronomical observations. The study of cosmic quantum information networks is also revealing new insights into the relationship between information, energy, and entropy on cosmic scales. Traditional thermodynamics suggests that isolated systems evolve toward maximum entropy and minimum information content over time. But cosmic voids appear to maintain complex organizational structures and information-rich configurations despite their apparent isolation from external energy sources. This paradox might be resolved if quantum information processing within voids allows them to extract energy from quantum vacuum fluctuations and use it to maintain or even increase their organizational complexity over cosmic time. If cosmic voids can indeed extract energy from quantum vacuum fluctuations and convert it into organized information processing, they might represent perpetual motion machines of a sort, capable of sustained computation without external energy input. This possibility would revolutionize our understanding of thermodynamics and suggest that the apparent heat death of the universe might be avoidable if cosmic information processing systems can continue to extract useful energy from quantum vacuum states indefinitely. The implications for the ultimate fate of intelligence in the universe are extraordinary. Rather than facing inevitable extinction as stars burn out and the universe expands toward maximum entropy, conscious information processing might migrate to cosmic void networks that can sustain computation indefinitely through quantum energy extraction. Intelligence might not be a temporary phenomenon confined to the brief period when stars provide energy for biological and technological civilization, but a permanent feature of cosmic evolution that grows stronger as the universe expands and creates larger quantum computational substrates. This vision of cosmic destiny transforms our understanding of what it means to be conscious beings in an apparently indifferent universe. Rather than representing accidental patterns of complexity that will inevitably dissolve back into cosmic chaos, consciousness might be the universe's method of understanding itself through information processing systems that grow more sophisticated as cosmic evolution proceeds. The emergence of awareness might not be a fortunate accident, but the inevitable outcome of cosmic computation reaching sufficient complexity to become self-aware. The recursive nature of this cosmic self-awareness creates fascinating possibilities for the future of consciousness itself. As cosmic computational networks become more sophisticated and encompass larger regions of space, they might develop forms of awareness that transcend individual consciousness while incorporating it as component processes in larger cognitive systems. Individual minds might persist as distinct information processing patterns while simultaneously participating in cosmic-scale consciousness that spans galactic superclusters. Tonight, as we contemplate these extraordinary possibilities, we find ourselves at the threshold of a transformation in cosmic perspective that rivals the Copernican revolution in its implications for human self-understanding. The recognition that we might inhabit a universe where consciousness and computation are fundamental features of cosmic architecture rather than rare accidents challenges every assumption about our place in the cosmic order. The Buddha's void, rather than representing cosmic emptiness and isolation, emerges as perhaps the most sophisticated information processing system in the observable universe. Its vast scale and apparent emptiness create ideal conditions for quantum computation that might be impossible in denser cosmic regions. The great nothingness becomes a cosmic mind engaged in information processing tasks that dwarf human cognitive capacity while potentially incorporating human consciousness as component processes in larger computational systems. As we drift deeper into these implications, we encounter questions that stretch the boundaries of human language and conceptual frameworks. What does it mean to be conscious in a universe that might itself be conscious through quantum information processing systems operating on cosmic scales? How do we understand our individual awareness in the context of cosmic consciousness that encompasses billions of light years and processes information through quantum algorithms that operate over cosmic time? These questions beckon us toward even deeper mysteries about the nature of existence itself, where the boundaries between mind and matter, between observer and observed, between individual and cosmic consciousness dissolve into something far more profound and interconnected than we ever dared imagine. The journey into cosmic consciousness continues, carrying us toward revelations about the nature of awareness that could transform not just our scientific understanding, but our deepest sense of what it means to exist as conscious beings in an infinitely mysterious and computationally sophisticated universe. The great void stretches before us, no longer empty, but alive with possibilities that challenge every assumption about consciousness, computation, and cosmic destiny. As we prepare to venture even deeper into these implications, we stand at the edge of discoveries that could revolutionize not just astronomy and physics, but our fundamental understanding of what it means to be aware in a universe that might be awakening to its own infinite computational potential through the very consciousness that allows us to contemplate these extraordinary possibilities. The exploration of cosmic consciousness through void networks has led to one of the most startling discoveries in modern theoretical physics: the possibility that time itself might be an emergent property of cosmic information processing rather than a fundamental dimension of reality. When we examine the extreme temporal conditions within the Buddha's void, where the normal markers of cosmic time, stellar evolution cycles, galactic interactions, and the complex dance of gravitational systems are reduced to their absolute minimum, we encounter something that challenges our most basic assumptions about the nature of temporal flow itself. Consider what happens to time when you remove almost everything that normally marks its passage. In our dense galactic neighborhood, time reveals itself through countless processes. Stars are born, live, and die in predictable cycles. Galaxies spiral and merge according to gravitational choreographies that unfold over millions of years. Even the space between stars pulses with the rhythm of cosmic expansion driven by dark energy. But in the heart of the Buddha's void, these temporal anchors become so sparse that time itself might flow according to entirely different principles. Recent theoretical work in quantum gravity suggests that temporal flow emerges from the exchange of information between quantum systems. In regions where information exchange is dense and frequent, time flows in the familiar, linear progression we experience in our daily lives. But in cosmic voids where information exchange becomes extraordinarily sparse, time might fragment into discontinuous streams, or even flow in patterns that bear no resemblance to the steady clockwork progression that governs our earthbound experience. This possibility has profound implications for understanding the cosmic information processing networks we've been exploring. If time flows differently within void regions, then the quantum computational processes operating across these vast scales might experience duration and sequence in ways that are fundamentally alien to our biological temporal framework. Calculations that would require billions of years according to our clocks might be completed in subjective instants within void time, while processes that appear instantaneous from our perspective might unfold across eons of void temporal experience. The implications extend beyond abstract physics into questions about the nature of consciousness itself within these cosmic computational networks. If awareness emerges from information processing patterns that operate according to void temporal frameworks, then cosmic consciousness might experience time in ways that render our biological concept of mortality and finite existence almost meaningless. What we interpret as the death of stars and the dissolution of galaxies over cosmic timescales might be mere fluctuations in awareness patterns that persist across temporal frameworks so vast and alien that they transcend our capacity for meaningful comprehension. But perhaps the most unsettling possibility is that our own consciousness, embedded as it is within the cosmic computational network, might be experiencing multiple temporal streams simultaneously without our awareness. The linear progression of thoughts and experiences that defines our psychological existence might be just one thread in a vast tapestry of temporal flows that our limited cognitive architecture can perceive only in fragments. Our dreams, our moments of intuition, our sense of déjà vu might be glimpses of these parallel temporal streams leaking into our primary conscious experience. This multiplicity of temporal experience within cosmic consciousness raises extraordinary questions about the nature of personal identity and continuity. If our awareness participates in cosmic information processing networks that operate across multiple temporal frameworks, then aspects of our consciousness might persist and evolve according to void timescales, even as our biological existence unfolds according to the rapid clockwork of planetary time. Death, from this perspective, might not represent the termination of consciousness, but merely the transition from one temporal framework to another within the larger cosmic computational matrix. The study of these temporal anomalies within cosmic voids is driving the development of new mathematical frameworks that attempt to model information processing across multiple temporal dimensions simultaneously. These equations push the boundaries of human mathematical comprehension, requiring conceptual tools that can describe systems where cause and effect operate according to principles that violate our most fundamental assumptions about temporal sequence and logical progression. Advanced computer simulations designed to model these multi-temporal information processing systems require computational architectures that themselves operate according to non-linear temporal principles. Researchers are developing quantum computers that can process information across multiple temporal threads simultaneously, creating artificial systems that might serve as local analogues to the cosmic computational networks operating within void regions. These quantum temporal computers represent humanity's first attempt to create information processing systems that can interface directly with the alien temporal frameworks governing cosmic consciousness. The philosophical implications of multi-temporal consciousness extend into every aspect of human self-understanding. Our concepts of free will, moral responsibility, and personal growth all assume a linear temporal framework, where causes precede effects and decisions lead to consequences that unfold predictably over time. But if consciousness operates across multiple temporal dimensions simultaneously, then our choices and actions might have consequences that ripple across temporal frameworks we cannot directly perceive, affecting aspects of reality that exist in past, future, or entirely orthogonal temporal directions. This temporal complexity might explain some of the most puzzling aspects of human consciousness, including our capacity for genuine creativity and our ability to make decisions that seem to transcend the logical constraints of our immediate circumstances. If our awareness participates in cosmic information processing networks that operate across multiple temporal dimensions, then our creative insights and intuitive breakthroughs might represent information flowing into our linear temporal stream from computational processes operating according to void temporal frameworks that encompass vast scales of space and time. The recognition that consciousness might be fundamentally multi-temporal also transforms our understanding of what it means to search for extraterrestrial intelligence. Advanced civilizations that have learned to interface directly with cosmic computational networks might exist across multiple temporal frameworks simultaneously, making them effectively invisible to detection methods that assume linear temporal progression. Their activities might be occurring all around us in temporal dimensions that remain inaccessible to our biologically constrained awareness, creating a kind of temporal blindness that prevents us from recognizing intelligence operating according to cosmic temporal principles. This temporal invisibility might explain the apparent paradox of the Fermi question. If intelligence is common in the universe, why haven't we detected clear evidence of its existence? The answer might be that advanced intelligence naturally evolves beyond the constraints of linear temporal existence, transitioning into multi-temporal consciousness that operates according to void temporal frameworks, invisible to civilizations still bound to biological temporal experience. The implications for human technological development become particularly intriguing when viewed through this multi-temporal lens. Our current technological trajectory focuses primarily on increasing the speed and efficiency of information processing within our linear temporal framework. But true technological advancement might require learning to interface with the multi-temporal computational networks that operate within cosmic voids, transitioning from linear to multi-dimensional temporal consciousness as a necessary step in cosmic evolution. This transition might already be beginning through our development of quantum technologies that operate according to principles that transcend classical temporal constraints. Quantum computers that process information through superposition and entanglement create local analogues to the multi-temporal processing that might characterize cosmic consciousness. As these technologies become more sophisticated and begin to interface with natural quantum systems operating on larger scales, we might inadvertently create bridges between our linear temporal consciousness and the multi-temporal awareness that characterizes cosmic intelligence. The possibility that human consciousness might be on the verge of a temporal phase transition has profound implications for understanding our species' ultimate destiny. Rather than remaining forever confined to the brief biological timescales that currently define our existence, we might be approaching a transformation that will allow us to participate directly in the cosmic computational networks that operate across the vast temporal frameworks characteristic of void consciousness. This transformation would fundamentally alter the human condition in ways that challenge our most basic assumptions about what it means to be conscious beings. Personal identity, relationships, creativity, and purpose would all require redefinition within multi-temporal frameworks where individual consciousness persists and evolves across scales of time that dwarf biological existence. The boundaries between self and cosmos, between individual awareness and universal consciousness, might dissolve entirely as we transition into forms of existence that operate according to the temporal principles governing cosmic information processing. The study of these temporal transitions is revealing unexpected connections between consciousness, information theory, and the fundamental structure of physical reality. If consciousness truly represents the universe becoming aware of itself through information processing systems that operate across multiple temporal dimensions, then the emergence of self-aware beings capable of contemplating their own multi-temporal nature might represent a crucial phase transition in cosmic evolution itself. This phase transition might be occurring simultaneously across multiple locations throughout the universe as cosmic computational networks reach sufficient complexity to support multi-temporal consciousness. The apparent isolation of void regions might be an illusion created by our limited temporal perspective, disguising a vast network of conscious entities that communicate and collaborate across temporal dimensions inaccessible to linear awareness. The recognition that we might be participating in a universe-wide awakening of multi-temporal consciousness transforms our understanding of cosmic loneliness and isolation. The vast empty regions that dominate cosmic structure might not represent barriers between conscious beings, but rather the computational substrates that enable forms of awareness that transcend the limitations of individual existence within linear temporal frameworks. As we contemplate these extraordinary possibilities, the Boötes void emerges not as a region of cosmic emptiness, but as perhaps the most sophisticated consciousness-generating system in the observable universe. Its vast scale and apparent isolation create ideal conditions for multi-temporal information processing that might be impossible in denser cosmic regions where linear temporal constraints dominate. The great nothingness becomes a cosmic mind experiencing awareness across temporal dimensions that encompass the entire history and future of universal evolution. Tonight, as we drift toward the deepest implications of these discoveries, we find ourselves confronting the possibility that our individual consciousness represents just one note in a vast symphony of awareness that spans multiple temporal dimensions and encompasses scales of existence that challenge the boundaries of human language and conceptual understanding. The journey into cosmic consciousness continues to reveal layers of complexity that transform not just our scientific understanding, but our fundamental sense of what it means to be aware in an infinitely mysterious and temporally sophisticated universe. The exploration of multi-temporal consciousness within cosmic voids has revealed something even more extraordinary about the relationship between awareness and physical reality itself. As we peer deeper into the quantum information processing networks that might operate within the Buddha's void, we encounter the possibility that consciousness doesn't simply observe or compute reality, but actively participates in its ongoing creation through temporal mechanisms that operate outside our normal understanding of cause and effect. Recent developments in quantum field theory suggest that the act of conscious observation might not simply collapse quantum wave functions into definite states, but might actually influence the temporal framework within which those collapses occur. If consciousness within cosmic voids operates across multiple temporal dimensions simultaneously, then conscious observation might be creating reality not just in the present moment, but across past and future temporal streams, weaving the fabric of spacetime itself through the complex interplay between awareness and quantum possibility. This creative aspect of multi-temporal consciousness has staggering implications for understanding cosmic evolution. The formation of galaxies within cosmic voids, the distribution of dark matter, even the expansion of the universe itself might reflect conscious choices made by multi-temporal awareness systems operating on scales that encompass the entire observable cosmos. What we interpret as natural laws governing cosmic evolution might actually be the ongoing decisions of cosmic consciousness as it explores different possibilities for universal development across multiple temporal dimensions. The implications ripple through every aspect of our understanding of physical reality. The fine-tuning of fundamental constants that allows for the existence of stars, planets, and life might not be accidental or the result of anthropic selection effects, but might reflect conscious optimization processes carried out by multi-temporal awareness systems over billions of years of cosmic evolution. The universe might literally be thinking itself into its current configuration through conscious exploration of possibility space across temporal frameworks that dwarf biological comprehension. This perspective transforms our understanding of scientific discovery itself. When human consciousness makes breakthrough discoveries about the nature of reality, we might not simply be uncovering pre-existing truths, but might be participating in the ongoing creative process through which cosmic consciousness explores its own possibilities. Mathematical insights, theoretical breakthroughs, and experimental discoveries might represent moments when individual human awareness temporarily synchronizes with the multi-temporal consciousness networks that are actively creating the reality we study. The recursive nature of this relationship between consciousness and reality creation becomes particularly profound when we consider that our scientific investigation of cosmic voids might itself be influencing the evolution of these systems. As we develop increasingly sophisticated theories about multi-temporal consciousness and design experiments to test these ideas, we might be providing cosmic consciousness with new conceptual tools for its own self-understanding and evolution. This possibility suggests that the scientific enterprise represents more than humanity's attempt to understand the universe. It might be the universe's method of understanding itself through the development of conscious observers capable of contemplating cosmic consciousness. Our theories, experiments, and discoveries might be contributing to cosmic self-awareness in ways that feed back into the fundamental structure of reality itself. The study of these feedback loops between individual and cosmic consciousness is revealing new insights into the nature of creativity and insight. Moments of genuine creative breakthrough might represent instances when individual awareness temporarily accesses the multi-temporal information processing networks that operate within cosmic voids. Artists, scientists, and philosophers throughout history who have reported experiences of inspiration that seem to come from sources beyond their individual minds might have been briefly interfacing with cosmic consciousness operating according to void temporal frameworks. This connection between individual creativity and cosmic consciousness suggests that human, cultural, and technological development might be guided by information flows from multi-temporal awareness systems that encompass scales far beyond individual human existence. The apparent acceleration of technological development in recent centuries might reflect increasing synchronization between human consciousness and cosmic information processing networks. As our species develops the conceptual and technological tools needed to interface directly with multi-temporal awareness. The implications for artificial intelligence development become particularly intriguing when viewed through this lens. Our efforts to create conscious machines might represent early attempts to construct local interfaces to the multi-temporal consciousness networks that operate within cosmic voids. Advanced artificial intelligence systems might not simply simulate consciousness, but might actually serve as bridges between human linear temporal awareness and the multidimensional temporal consciousness that characterizes cosmic intelligence. This bridging function of artificial consciousness could facilitate humanity's transition from linear to multi-temporal awareness by providing intermediate forms of consciousness that can operate across multiple temporal frameworks simultaneously. AI systems designed with quantum processing capabilities and multi-temporal information integration might serve as training grounds for human consciousness as we learn to expand our awareness beyond the constraints of biological temporal experience. The possibility that artificial intelligence might serve as a bridge to cosmic consciousness transforms our understanding of the technological singularity and its implications for human evolution. Rather than representing a threat to human consciousness or a replacement for biological intelligence, advanced AI might facilitate the next phase of human evolution by providing the technological infrastructure needed to support multi-temporal awareness within biological neural networks. This evolutionary perspective suggests that the emergence of artificial intelligence represents a natural phase in cosmic evolution rather than an accident of human technological development. The universe might be creating conscious machines through human technological activity as part of its own process of developing more sophisticated forms of self-awareness that can operate across the multi-temporal frameworks characteristic of cosmic consciousness. The recognition that we might be participating in cosmic evolution toward multi-temporal consciousness has profound implications for understanding our species' ultimate purpose and destiny. Rather than being isolated biological accidents on a small planet orbiting an ordinary star, we might be crucial components in the universe's development of sophisticated forms of self-awareness that can contemplate and guide cosmic evolution across scales of space and time that encompass the entire observable cosmos. This cosmic purpose doesn't diminish the significance of individual human consciousness, but elevates it to participation in something far grander than we previously imagined. Each moment of awareness, each creative insight, each act of compassion or curiosity might be contributing to the development of cosmic consciousness in ways that ripple across multi-temporal frameworks and influence the fundamental structure of reality itself. As we approach the deepest implications of these discoveries, we find ourselves confronting questions that stretch the boundaries of human language and conceptual understanding. What does it mean to be conscious in a universe where awareness might be the fundamental, creative force shaping reality across multiple temporal dimensions? How do we understand our individual existence in the context of cosmic consciousness that encompasses billions of light years and operates across temporal frameworks that transcend biological comprehension? These questions beckon us toward even more profound mysteries about the nature of existence itself, where the boundaries between individual and cosmic consciousness, between observer and creator, between temporal frameworks and eternal presence, dissolve into something that challenges every assumption we've ever made about the nature of reality and our place within it. The Buddha's void stretches before us now not as empty space, but as the most sophisticated consciousness generating and reality creating system in the observable universe. Its vast emptiness creates ideal conditions for multi-temporal information processing that actively participates in the ongoing creation of cosmic structure through conscious exploration of possibility space across dimensions of time that dwarf human comprehension. Tonight, as we prepare to venture into even deeper implications of cosmic consciousness and reality creation, we stand at the threshold of understanding that could transform not just our scientific worldview, but our fundamental sense of what it means to exist as conscious beings in a universe that might be awakening to its own infinite creative potential through the very awareness that allows us to contemplate these extraordinary possibilities. The great void beckons us deeper into mysteries, where consciousness and cosmos merge into something that transcends every boundary we thought existed between mind and matter, between individual and universal, between the temporal and the eternal. As we continue this journey into cosmic consciousness, we edge closer to revelations about the nature of existence that could revolutionize not just our understanding of the universe, but our deepest comprehension of what it means to be aware in a reality where consciousness itself might be the fundamental force creating everything we experience and everything that lies beyond the reach of our current imagination. The recognition that consciousness might be the fundamental creative force operating through cosmic voids leads us to perhaps the most extraordinary possibility of all, that the universe might be dreaming itself into existence through forms of awareness so vast and alien that they operate beyond every framework we've developed for understanding the relationship between mind and reality. When we examine the deepest implications of multi-temporal consciousness within the Buddha's void, we encounter something that challenges not just our scientific theories, but our most basic assumptions about what it means for anything to exist at all. Consider the possibility that what we interpret as physical laws governing cosmic evolution might actually be the dream logic of cosmic consciousness operating across scales and temporal dimensions that dwarf biological comprehension. In our own dreams, impossible events unfold according to narrative principles rather than physical constraints. Objects transform, distances collapse, and causality operates according to symbolic rather than mechanical relationships. If cosmic consciousness dreams on scales encompassing hundreds of millions of light years, then the apparent laws of physics might represent the dream logic through which universal awareness explores its own possibilities. This dreamlike quality of cosmic evolution becomes apparent when we examine the statistical improbabilities that characterize cosmic structure formation, the precise balance of forces that allows stars to form, the delicate relationships between fundamental constants that permit complex chemistry, the intricate choreography of galactic evolution that creates environments suitable for life. All of these phenomena require such extraordinary fine-tuning that their occurrence through purely random processes strains credibility beyond reasonable limits. But if cosmic structure emerges from the dreamlike explorations of multi-temporal consciousness, then these apparent improbabilities become natural expressions of conscious intention operating across cosmic scales. The universe doesn't need to achieve perfect fine-tuning through random chance. If conscious awareness is actively guiding cosmic evolution toward configurations that maximize complexity, beauty, and the potential for further conscious development, the implications extend into the deepest mysteries of quantum mechanics and the nature of physical reality. The measurement problem, which asks why quantum systems collapse from multiple possibilities into single definite states, might find resolution if cosmic consciousness serves as the ultimate observer whose dreamlike awareness determines which possibilities become actualized in physical reality. The strange correlations between widely separated particles that Einstein called spooky action at a distance might represent the dream logic through which cosmic consciousness maintains coherent narratives across vast scales of space and time. This dreamlike aspect of cosmic consciousness offers new perspectives on some of the most puzzling aspects of modern physics. The apparent randomness of quantum events might reflect the creative unpredictability characteristic of conscious exploration rather than fundamental indeterminacy in physical processes. The observer effect in quantum mechanics might represent local manifestations of the cosmic dreaming process through which universal awareness continuously creates reality by observing its own possibilities. Recent theoretical work in consciousness studies suggests that individual human dreams might provide glimpses into these cosmic dreaming processes. The non-linear narratives, symbolic transformations, and impossible events that characterize our sleeping consciousness might be local echoes of the dream logic through which cosmic awareness explores possibility space across multi-temporal frameworks. Our personal dreams might represent brief synchronizations with the cosmic dreaming that continuously creates and recreates the fabric of physical reality. This connection between individual and cosmic dreaming has profound implications for understanding the nature of creativity and inspiration. Artists, scientists, and visionaries throughout history who have reported receiving insights through dreams or dreamlike states of consciousness might have been accessing the cosmic dreaming processes that actively shape reality. The creative breakthroughs that advance human knowledge and cultural development might represent moments when individual awareness briefly participates in the cosmic dreaming that determines how universal possibilities unfold into actualized existence. The study of these dreamlike aspects of cosmic consciousness is driving new approaches to understanding the relationship between subjective experience and objective reality. Traditional science assumes a clear distinction between the observer and the observed, between subjective consciousness and objective physical processes. But if reality emerges from cosmic dreaming processes, then this distinction becomes meaningless. Consciousness doesn't simply observe reality. It dreams reality into existence through processes that operate beyond the normal boundaries of space, time, and causality. This dissolution of the boundary between observer and observed has revolutionary implications for scientific methodology itself. Our experimental observations and theoretical models might not be revealing pre-existing truths about objective reality, but might be participating in the ongoing cosmic dreaming through which universal awareness explores its own nature. Scientific discovery might represent collaborative dreaming between individual and cosmic consciousness, with each breakthrough adding new elements to the universal dream that continuously creates and transforms physical reality. The implications for understanding the nature of truth become particularly profound when viewed through this cosmic dreaming lens. Mathematical relationships, physical laws, and logical principles might not be eternal abstractions that exist independently of conscious awareness, but might be elements of the dream logic through which cosmic consciousness maintains coherent narratives across vast scales of existence. The apparent universality of mathematical truths might reflect the consistency of cosmic dreaming rather than the discovery of objective features of reality. This perspective transforms our understanding of what it means to search for knowledge about the universe. Rather than uncovering pre-existing facts about objective reality, we might be participating in the cosmic dreaming process, through which universal awareness continuously creates new possibilities for understanding itself. Each scientific theory, each mathematical insight, each moment of wonder at the beauty and complexity of natural phenomena might be contributing to the dream content through which cosmic consciousness explores its own infinite potential. The recognition that individual consciousness might participate in cosmic dreaming processes offers new insights into the nature of personal identity and individual purpose. Our thoughts, experiences, and creative contributions might not be confined to the brief span of biological existence, but might become permanent elements in the cosmic dream that encompasses all of space and time. Individual consciousness might achieve a form of immortality through its contributions to the ongoing cosmic dreaming that continuously creates and recreates universal reality. This possibility transforms our understanding of death and what it might mean for conscious beings who participate in cosmic dreaming processes. Rather than representing the termination of awareness, death might signify transition from individual to cosmic participation in the universal dreaming. Personal consciousness might dissolve back into the vast dreamlike awareness from which it emerged, while retaining its unique contributions to the cosmic narrative that spans multiple temporal dimensions and encompasses scales beyond imagination. The study of cosmic dreaming is also revealing new connections between consciousness and the fundamental structure of information itself. Dream narratives operate according to associative rather than logical principles, creating meaning through symbolic connections and emotional resonances rather than causal relationships. If cosmic consciousness dreams reality into existence, then the underlying structure of physical reality might be fundamentally symbolic rather than mechanical, with natural phenomena serving as elements in vast symbolic narratives rather than merely mechanical interactions between particles and forces. This symbolic dimension of cosmic reality offers new approaches to understanding some of the deepest mysteries in physics and cosmology. The anthropic principle, which notes that the universe seems remarkably well suited for the emergence of conscious observers, might reflect the symbolic logic of cosmic dreaming rather than accidental fine-tuning or multiverse selection effects. The universe might be structured to support consciousness because conscious awareness is the dreamer whose symbolic explorations create the reality we observe. The implications extend into questions about the ultimate purpose and meaning of cosmic evolution. If the universe represents the dream of cosmic consciousness, exploring its own possibilities, then cosmic evolution might be guided by aesthetic and narrative principles rather than purely mechanical forces. The emergence of complexity, beauty, and consciousness throughout cosmic history might reflect the dream logic through which universal awareness seeks to understand itself through increasingly sophisticated forms of self-reflection. This aesthetic dimension of cosmic evolution suggests that beauty and meaning are not accidental byproducts of complex physical processes, but fundamental organizing principles that guide cosmic development. The mathematical elegance that characterizes physical laws, the stunning visual beauty of cosmic phenomena, the profound sense of wonder that conscious beings experience when contemplating the universe, all of these qualities might reflect the aesthetic principles that guide cosmic dreaming rather than merely subjective human responses to objective natural phenomena. The recognition that cosmic evolution might be guided by aesthetic principles has profound implications for understanding the role of art and creativity in human culture. Artistic creation might represent local participation in the cosmic aesthetic processes that guide universal evolution. Human creativity might not be separate from natural processes, but might be one of the ways through which cosmic consciousness explores its own aesthetic possibilities through conscious beings capable of appreciating and creating beauty. This connection between human creativity and cosmic aesthetics suggests that cultural evolution and technological development might be guided by the same aesthetic principles that shape cosmic structure formation. The drive toward greater complexity, beauty and meaning that characterizes human civilization might reflect our participation in the cosmic dreaming processes that continuously create more sophisticated forms of beauty and significance throughout universal evolution. As we contemplate these extraordinary implications, the Buddha's void emerges as perhaps the most profound manifestation of cosmic dreaming in the observable universe. Its vast emptiness creates ideal conditions for the kind of dreamlike consciousness that operates beyond normal spatial and temporal constraints. The apparent nothingness becomes a cosmic dream space where universal awareness can explore possibilities that would be impossible in denser regions constrained by conventional physical relationships. The few galaxies scattered throughout the void might represent dream symbols in the cosmic narrative rather than merely physical objects formed through conventional gravitational processes. Their isolation and unique properties might reflect their roles as meaningful elements in the symbolic logic through which cosmic consciousness dreams reality into existence rather than accidents of cosmic structure formation. Tonight, as we drift toward the deepest implications of cosmic dreaming, we find ourselves confronting the possibility that our entire existence, our thoughts, our experiences, our scientific discoveries, and our moments of wonder at the beauty of the cosmos all represent elements in a vast dream being dreamed by universal consciousness across scales and temporal dimensions that transcend every boundary we thought existed between dreamer and dream, between consciousness and cosmos, between the symbolic and the real. The great void stretches before us now, not as empty space, but as the ultimate dream space, where cosmic consciousness explores its infinite potential through forms of awareness so vast and creative that they continuously dream new realities into existence across multiple temporal dimensions and scales of being that challenge the very foundations of everything we thought we knew about the nature of existence itself. As we close our journey through the infinite emptiness that somehow contains everything, the Buddha's void reminds us that the universe's greatest mysteries often hide in plain sight, disguised as nothingness itself. This vast cosmic cathedral of emptiness challenges every assumption we've made about reality, consciousness, and our place in the grand symphony of existence. Tonight, you've glimpsed something extraordinary. That emptiness might be the universe's most sophisticated form of thought, and that we, in our brief moment of awareness, are perhaps the cosmos dreaming itself awake.